Hi, I'm Martin for the VGS tutorial series at UCLA. In a previous video, we've seen how to manipulate a 2D structures and how to create a truss. And in this video, I will introduce you to the creation of a three-dimensional system based on a thin truss, like this, and how to manage the supports of such a system with VGS. So I will explain in detail how to assemble the truss together, but also how to use the supports component and the text output of the evaluate equilibrium component to avoid hyperstaticity. So here we are in the Rhino environment. I will explain the construction of this 3D truss. So a three-dimensional structure like this one needs to be braced to stand and resist different horizontal forces. I will just use grasshopper to show you the structure more easily. So let's start with our initial truss that we can see in the right view in the ZY plane. So this type of truss is called a thin truss. And we've added a vertical bar to this truss to turn it into a portal frame there. So this truss will support vertical loads. And we notice that we added two diagonals to build the frame and brace the structure. This allows to withstand the lateral forces in the y direction, as for example wind forces. Then this truss also needs to be braced in the x direction. So let's examine the xy plane. The truss will resist the x direction thanks to diagonals there. And we notice that one cell doesn't have any diagonals. It's because that it will lead to hyperstaticity. So all of this forms a stabilization span essential to the stability of the whole system. And next, we need to brace the XY plane. So to do this, we connect each truss to diagonals, as we can see in the front view there. And we see that in the left cell, this one, we added an additional diagonals to improve the bracing. And the same applies to the supports bar, where we also added a diagonals there. Now, let's move to the grasshopper environment. To use VGS, we need to define the structural geometry as edges, actually a system of bars, then support conditions and loading. So I use first a curve component, and as entry I choose all the lines of my model, like this one, there, and then I press enter. And so this is my edges. Next, we need to define the loads. It is the same as for edges. For my loads, I select the multiple points, and I'm going to select all the points of my model where my loads are going to be applied. So there, all of these points are my loads. Okay. And I also need to define the load intensity as a vector. So in my example, I can adapt the magnitude of loads using a slider. Then we need to define the supports. As we can see on the model, there is two lines of supports. So I'm going to select the first row of points and use them as bind supports. So for this, the points are going to be blocked in every direction. So they're X, Y, Z. And as we can see on the model, they are blocked. Okay. So this guarantee that this part of the structure does not move in any direction. Then, as this part of the structure works as an isostatic portal frame, we are going to select the other row of points there. Okay. And for this, the points will be blocked in the X and Z direction. So as we can see there, so this line should not be fixed in every direction to avoid the hyperstaticity. Now we can look at the VGS analysis of the structure. If you are unable to calculate the structure with VGS, it is probably because your structure isn't isostatic. So one way to check this is by using a panel component. I'm going to show you the evaluate equilibrium component, and I'm going to plug it in the panel component. So as we can see in the panel, it shows us that there are 0 internal mechanism and no self-stress are needed, which confirms that our structure is indeed isostatic. Now I'm going to preview this off, and we can now see the shape diagram provided by the VGS analysis there. So it shows the different forces acting on various parts of the truss, where in fact red represents tension elements and blue represents compression elements. So next we can generate the force diagram. So to generate the force diagram, you need to use a button there and connect it to the reset input on the component. In some cases, where there are many elements to calculate, as it is the case for this model, this process may take some time. So don't panic if grasshopper takes a while to get back up and running. Besides the video, I've also generated the force diagram, which we can see here. So it shows all the force vectors in the system along with their intensities there. And I use the locate diagram component to move it around for better visibility. So by looking at the length of each vector, we can understand the relative strength of the forces. This helps later on when we make connections or size the elements of the structure. Another way to visualize the force diagram using the shape diagram is by selecting the node we want to see. So for example, by using a slider there, I can connect it to both components here, and which allow us to access the bars that are linked to each other. I can move the slider, as you can see here, to analyze each node individually. So for example, for node 0, I can find it in the shape diagram here and see the intensity of the forces in the force diagram next to it. So this helps me better understand and visualize the forces around this node there. So that's it for this tutorial video. We covered how to brace these 3D isostatic structures and how to manage the associated supports. I hope it was helpful. Thank you.